Today we're going to explore one of the most elegant experiments in physics history, how Robert Millikan established that electric charge is quantized. This isn't just a historical curiosity, it's a masterclass in extracting signal from noise. The question Millikan faced in 1909 was profound. Is electric charge continuous, like water, or does it come in discrete packets? Let me describe the apparatus. Millikan suspended tiny oil droplets between two charged metal plates. The droplets pick up charge from ionized air. By adjusting the voltage between the plates, Millikan could balance the electric force against gravity, holding a droplet nearly stationary. The key insight was this: if charge is quantized, then all droplets should carry charges that are integer multiples of some fundamental unit. But here's the problem. The measurements are incredibly noisy. The droplets are microscopic, they undergo Brownian motion, and determining the exact charge requires multiple indirect measurements. The charge Q equals mg times the quantity versus F plus VR divided by VRE, where m is the droplet mass, g is gravity, Vf is the falling velocity, Vr is the rising velocity, and E is the electric field. Each of these variables has uncertainty. The mass depends on the droplet radius cubed, so a small error in radius gives a large error in mass. Let's walk through what a student would actually do. You start by recording raw measurements for droplet number 1. You measure how long it takes the droplet to rise and fall over a fixed distance. Notice the scatter. Trial 1 gives 12.3 seconds. Trial 2 gives 11.9 seconds. Trial 3 gives 12.6 seconds. Question: why do we need multiple trials? Answer: because random thermal motion and air currents cause fluctuations. By averaging, we reduce the uncertainty. We convert time to velocity. If the distance is 1 millimeter, then a rise time of 12 seconds gives a velocity of about 0.083 millimeters per second. Now we need to calculate the droplet radius and mass. This requires measuring the terminal velocity when falling without the electric field. The radius r equals the square root of 9 eta versus F divided by 2 rho g, where eta is the viscosity of air, rho is the density of oil. For typical conditions, oil density is about 900 kilograms per cubic meter. Air viscosity is 1.8 times 10 to the negative 5 Pascal seconds. The mass is 4/3 pi r cubed rho. Notice the r cubed. This is why radius errors matter so much. Let's do a back-of-the-envelope calculation. Say we measure a falling velocity of 0.05 millimeters per second. Plug it into the formula, we get a radius of about 1.3 times 10 to the negative 6 meters, or 1.3 micrometers. The mass is about 8 times 10 to the negative 15 kilograms. That's 8 femtograms, incredibly tiny. Now we use the rise and fall velocities along with the electric field to calculate the charge. For droplet 1, suppose we calculate a charge of 3.2 times 10 to the negative 19 coulombs. Here's where the real work begins. You must repeat this entire process for dozens of droplets. Here's what the data might look like. Droplet 1 has 3.2 times 10 to the negative 19 coulombs. Droplet 2 has 6.5. Droplet 3 has 4.8, and so on. Each has an uncertainty. Notice something important. The values are scattered, but they're not uniformly distributed. There seems to be clustering. Let's visualize this. We'll make a histogram where the horizontal axis is charge and the vertical axis is frequency. Here's the histogram. Notice the peaks. One around 1.6, another around 3.2, another around 4.8, then 6.4, 8.0, and 9.6. The clustering is the key observation. It suggests that all charges are multiples of some fundamental unit. Now we test the hypothesis rigorously. If charge is quantized, then all measured charges should satisfy Q equals n times E, where n is an integer and E is the elementary charge. The equation is Q equals NE, where n is in the set 1, 2, 3, and so on. One method is to calculate the differences between all pairs of charges. If quantization is real, these differences should also be integer multiples of E. Look at the differences. When we subtract Q1 from Q2, we get 3.3. When we subtract Q1 from Q3, we get 1.6. The smallest common difference that appears repeatedly is 1.6 times 10 to the negative 19 coulombs. This suggests that the elementary charge is 1.6 times 10 to the negative 19 coulombs. Now we check whether all our measured charges are consistent with this hypothesis. For each droplet, we divide the measured charge by 1.6 to get a predicted n value. Then we multiply n times e to get the predicted charge. The residuals are small, all within our measurement uncertainty. Question: could this pattern be a coincidence? Answer: we can calculate the probability. If charges were random, the chance of getting this level of clustering is astronomically small. A rigorous statistical test is the chi-squared goodness of fit. You compare the observed distribution to what you'd expect from the quantization hypothesis. Chi squared equals the sum of OI minus EI, quantity squared, divided by EI, where OI is the observed frequency and EI is the expected frequency. A critical step. We must stress test the conclusion, change the experimental conditions, and see if the same fundamental unit emerges. First variation. Change the electric field strength. Use 300 volts instead of 500 volts. Second variation. Use different oils. This changes the droplet density and viscosity corrections. Third variation. Change the plate separation. This affects the field uniformity. If charge quantization is a fundamental property of nature, then the value of E should remain the same regardless of these experimental details. Here are results from different conditions. The calculated E value stays within 1% across all variations. This consistency is powerful evidence. The ultimate test of any scientific hypothesis is prediction. If we've correctly identified the fundamental charge unit, we should be able to predict where new measurements will cluster. The prediction is clear. Any new droplet we measure should have a charge equal to n times 1.6 times 10 to the negative 19 coulombs, where n is a positive integer. We perform a blind test, measure 20 new droplets, analyze them, and only then compare to the prediction. Here's the result. The red dashed lines show the predicted positions based on our hypothesis. The green dots show where the new measurements actually landed. The agreement is remarkable. Every single new measurement falls within the experimental uncertainty of a predicted position. This is not just confirmation, it's validation of the entire methodology. Millikan's original value was 1.592 times 10 to the negative 19 coulombs. The modern accepted value is 1.602176634 times 10 to the negative 19 coulombs, defined exactly since 2019. The elementary charge is 1.602176634 times 10 to the negative 19 coulombs, now defined exactly. Millikan's result was within 0.6% of the true value. This is extraordinary given the technology available in 1913. Why does this experiment still matter? It's not just historical. The methodology, extract sigma from noise, look for patterns, test predictions, is the foundation of modern experimental physics. The same approach is used in particle physics experiments at CERN. When physicists discovered the Higgs boson, they looked for a clustering of events at a specific energy. In astronomy, exoplanets are detected by looking for periodic dips in stellar brightness. The signal is tiny, but repeating patterns emerge from the noise. In biology, ion channels show quantized conductance, current flows in discrete steps when channels open and close. Same principle. Clustering reveals the fundamental unit. Let me summarize the key lessons from Millikan's workflow that apply to any quantitative science. First, uncertainty is not the enemy. You can extract profound truths from noisy data if you know what pattern to look for. Second, repetition reveals hidden structure. A single measurement tells you little. 10 measurements tell you much. 100 measurements can change physics. Third, always stress test your conclusions. Change the conditions. If the pattern persists, it's likely fundamental. Fourth, predictive power is the ultimate validation. Can you use your result to predict new observations? That's the gold standard. The deeper implication of charge quantization is profound. It tells us that matter is fundamentally discrete at the smallest scales. In 1913, some scientists still doubted whether atoms were real or just a useful fiction. Millikan's experiment was strong evidence that atoms exist and have discrete properties. Charge quantization foreshadowed the quantum revolution. If charge comes in packets, perhaps energy does too. This insight helped motivate Planck's quantum hypothesis. Let me leave you with this thought. Millikan started with a cloud of oil droplets, noisy data, and a controversial hypothesis. Through systematic measurement, careful uncertainty analysis, pattern recognition, and predictive testing, he established one of the fundamental constants of nature. This is the scientific method at its finest. Not a flash of genius, but patient, methodical work that transforms uncertainty into knowledge. You now have the conceptual tools to approach any quantitative problem this way. Record data with uncertainties, look for patterns, test hypotheses, make predictions. This is how science advances,